So a warm welcome to everyone on behalf of IEEE RITB. Today we have a talk on learning machine learning, preparing to contribute to the next industrial revolution. A distinguished lecture program which will be delivered by Dr. Sargur Srihari sir. A short biography of the sir. He is currently the Satish Dhawan Visiting Chair Professor of Indian Institute of Science. He is also a Sunny Distinguished Professor in the Department of Computer Science and Engineering at University of Buffalo, the State University of New York. Sir has also held the Rukmini Govindachar Chair in the School of CSA, IASC during 2018, a research laboratory that is deployed by the United States. Srihari sir has founded a research laboratory named CEDAR, which has developed the world's first automated system for reading handwritten postal addresses, which is currently deployed by the United States Postal Service, which saved hundreds of millions of dollars in labor costs, helping keep US postal rates low. And Sir has spent a decade developing AI and machine learning methods for forensics, focusing on pattern evidence such as latent prints, handwritings, and footwear impressions by quantifying the value of handwritten evidence to allow preventing such testimony in US courts. Sir teaches a trilogy of three courses, namely Introduction to Machine Learning, Deep Learning, and Probabilistic Graphical Models. His courses are publicly available and they're very famous. His lectures on deep learning summer school, which is held in Warsaw, Poland in 2019, and Leon, Mexico, are very famous. And then few of the honors for Srihari sir includes fellowship of Institute of Electronics and Telecommunication Engineering, that's IETE, and sir is also a fellow of IEEE, a fellow of International Association for Pattern Recognition, and he is a distinguished alumnus of Ohio State University College of Engineering. He has received an Excellence in Graduate Mentorship Award from the University of Buffalo in 2018. So it's a great honor to have sir with us today to deliver this great speech. So now I'll hand it over to sir to continue the session. A small note to all the participants. Sir will present his talk first, and after the talk is completed, we'll have a Q&A session. So over to sir.
Hey, thank you very much. Are you able to hear me properly?
Yes, sir.
Audio is fine? Okay. All right. Very good. So my talk is going to be about 45 minutes, maybe up to an hour. I'm purposely not going very long so that you can ask any questions. Along the way, if you want me to clarify something, feel free to ask me. Actually, a little bit of feedback like that would be welcome. So, so feel free to do that. So, hello?
Yes, sir.
Oh,
Able to hear you.
video is not there. Okay. So, what happened?
So your screen is visible. Can you please switch to slide
okay,
mode?
okay. All right. The video is now available, right?
Yes, sir. Yes, sir.
Okay. You're okay for me to get it going?
Yes, sir.
Okay. Very good. So, okay. So my talk today is different from the usual talks I give on what is machine learning, what is AI. This one is oriented towards teaching of machine learning or learning of machine learning. So what is involved is it like learning any other subject in let's say computer science or electrical engineering, where you can pick up some kind of a crash course on that topic and pick it up, or is there more to it? And I argue here that there is considerable amount of background to this, and I will kind of lay out my case for that. Okay, so what I will touch upon are the following topics. Okay, let me put it on full slideshow mode. Okay, all right, hopefully it's big enough. Okay, so I will begin with the ubiquity of artificial intelligence. You know, every newspaper every day had an article on AI until, of course, COVID came around. AI was always on the front burner for everybody. And then I'll move to the particular approach to AI called deep learning. And I will mention the underpinnings of deep learning, that what are the main components that are going to define the field, and then get into saying that machine learning has a heavy dose of calculus, of linear algebra, of probability and statistics, and computational complexity. So these are all the different ingredients that go into defining machine learning or deep learning algorithms. And then I will talk about what is the different kind of computer science that is needed to allow machine learning to be learned, and its disruptions to computer science, disruptions to software development itself. So this is the range of topics that I'll cover. All right, my first slide is just that AI is all around us. We are using it all the time. It is used to automate routine labor in searching. When we do a Google search, there is an underlying AI that is performing to figuring out, understanding what is it you might be looking for based on natural language entry or based on your behavior and based on other people's behavior and so on. So there are search engines such as Google and Baidu search and so on. I mentioned Baidu because it is founded by one of my students. Anyway, and then there is also understanding speech on our mobile phones or an Alexa device and so on. You know, got the speech understanding type of AI built into it. And there is also a lot of talk about autonomous vehicles that have built-in computer vision and AI to be able to drive on its own and so on. That is just a small fraction of the kind of applications of AI. I'm sure you could think of many, many more applications of AI. So the main point here is that AI is ubiquitous. It is all around us. And how was AI deployed? What went into it? Because it performed some intelligent things, and obviously it needs some knowledge and knowledge about the sounds that people utter, or for example, speech or computer vision, needs knowledge about what objects look like and so on. So definitely AI programs need knowledge, and so the challenge for AI developers is how do we get this intuitive and subjective knowledge, how to get this into the computer. And the early models of AI were known as knowledge-based approaches. And the knowledge-based approaches, hard-coded knowledge, saying, okay, it consists of this knowledge. This is what a stop sign looks like. And this kind of a sound means this, and so on. So a lot of those could be hard-coded and programmed into an AI program. Is just any other old program. All it has got is a whole bunch of if-then rules and so on to define this knowledge. But it had its own serious limitations, and in that there is so much knowledge. How do we keep on adding this knowledge when we get into new applications? How do we enter all this? So it was not scalable. So the solution to solving these kinds of problems was not just use machine learning in a rudimentary way, such as when you have these measurements, what is it? That's what machine learning was used for early on. It learns what these combinations of features corresponds to. We refer to it as machine learning or ML. But we went on to say, well, who gives you that kind of an input representation, and that has to be learned. Features also have to be learned, and so that AI systems can be used to rapidly adapt to new tasks. That the designing the features itself can take great human effort and can take decades for a community of researchers. And then came along deep learning, which says does not need programmer to have deep knowledge of the problem domain. So all these approaches is summarized in this one diagram. On the leftmost diagram is Try to minimize it on my screen here so I can see it myself. Okay. We have three block diagrams here in one slide. There is a rule-based system on the left, there's a classic machine learning in the middle, and there's representation learning in the right. And we refer to each of these as three paradigms of AI. The first one is a rule-based system, which goes from input to output through a hand-designed program. So that would be conventional logic going into an AI program, and we can call it AI if we want. But all the work was done by a human programmer to figure out how do I convert this into output? How do I say what this object is? In classic machine learning, what we do is, well, we design the hand designed features still. Human being does that, but the mapping from those features to the output is done by a simple machine learning program, which, for example, a nearest neighbor classifier or some other simple pattern recognition algorithm that would say when you have these types of inputs, in these types of features, that's what it means. So that is called classic machine learning here. And the approach that today all of AI is using is the third one, which is representation learning, where we go from input to features and we map from features to the output. So the gray boxes, features and mapping from features, are both determined automatically by machine learning programs. And a variation of that same one is in the last one called deep learning. And deep learning has additional layers of more abstract features and so on. But this is pretty much the same as the one to its left. Previous one had features, this one had simple features, additional layers for abstract features. So this is where we are, that today's machine learning, today's AI is largely about deep learning, which learns from the outside world what are the things that you need to extract from the outside world, whether it be an image or speech or some other abstract data. We need to first convert it into some type of representation and move from that representation to solve the task we have. Or solving the task may simply be recognition or recognizing what the word is said, what the object is, or predict the weather or whatever. Okay, so that is deep learning. And the kind of software and hardware architectures we used in deep learning is it is inspired by neural networks of the brain to build learning machines. So these are distributed networks that do this, which learn useful internal representation computed as a composition of learned features and functions. So this is what deep learning is about. It's some kind of a design. Those boxes we just saw in the previous slide. Take these raw inputs, convert them into features, into layers, and so on, and produce the output. But what is the architecture of that box? We're saying it's a deep learning architecture which is inspired by neural networks. And it doesn't. This definition of deep learning doesn't say how we achieve that. Simply is saying there is some type of network, maybe organized in terms of layers. And maybe by adding priors, it learns better high-level representation. So some human knowledge may go into it. And so the term deep learning is an aspirational definition. Just like AI itself is an aspirational definition. Machine learning is an aspirational definition. We would like it to be intelligent. We would like it to learn. We would like it to do deep learning in terms of learning layers and layers, higher level and next level and so on. So you can say this is what deep learning is about. It's a very broad statement, just like AI or machine learning. Okay, now how does learning, machine learning or deep learning differ from any other subject in computer science or electrical engineering or these technical subjects? And you can walk into a bookstore and you would find all these kinds of books for the general public, networking for dummies or HTML for dummies or coding for dummies and database development for dummies and multimedia for dummies and programming for dummies, graphic design for dummies. And there is even an artificial intelligence for dummies. All right, so you can see that there is some of these things people want to pick up some idea about what this subject is. And so it is possible to do that. And actually, I didn't know that there was a machine learning for dummies also. I looked at it. It is written by a person who's written a half a dozen other books. He also wrote AI for dummies. He also wrote multimedia for dummies. He wrote network for dummies. So it's kind of a mass production now that you name it, you can pick up some kind of a very high level newspaper style article in these kinds of works. Maybe there's a little bit more there. But I argue that more than any of these subjects, machine learning has a strong scientific basis to it. It is not something just to be picked up by just picking up one of these dummy textbooks. So we'll talk about really. So what is it that is special about machine learning? So now I will talk about where we are today and what are the underpinnings of this thing called deep learning, what is being used to solve these problems. Of course, it begins on the leftmost. It might look gross to some of you. It's an actual human brain that's being held in somebody's hands here. Brain. It's got all these neurons, and reputedly, the human brain has billions of neurons. Okay, billion, not million, billions, billions of neurons. I don't think it's quite trillions of neurons. It's of the order of billions. Being in India, I just learned yesterday what does 1 lakh crore mean, right? I saw that in the newspaper that the finance minister is authorizing 3 lakh crores. So I was wondering what does lakh crore mean? And lakh crore, it turns out to be exactly the same as 10 to the power of 5 times 10 to the power of 7. Lakh is 10 to the power of 5. Crore is 10 to the power of 7. So a lakh crore is 10 to the power of 12, which is exactly the same as a trillion. All right, so we might not have 1 lakh crore neurons. That would be trillion, but quite up there. It's several hundred crores. May not be 100,000, right? Anyway, so we are interested in neurobiology. Motivation came. What is this mass compute? And actually, we can name the people who got interested. Warren McCulloch and Walter Pitts. They were very interested in about the functioning of these billions of neurons in the brain. How does it function? And they found it's a very simple design that there are neurons connected to each other, and when they get enough stimuli from other neurons, when the sum of all these weighted somehow exceeds a threshold, it fires. Otherwise, it does not fire. And that's the basic connectivity that they found by doing some biological experiments on the brains by putting probes and so on. So it was really, they were interested in modeling it. They defined what's called as a formal neuron. It's the basic building block of the human brain and turns out to be the basic building block of today's deep learning designs. So that's the first part. Now, a lot of the designs that we have borrow many, many ideas from statistical physics, all things. That's a particular jar here that shows it has some gas inside it, and that gas may consist of a whole set of atoms, and the atoms are spinning left or right, and because it's interesting, it's binary, the spin of the atoms, and if they're all oriented in one direction, it has got high energy, and a high energy state of the gas, it has low probability. And so this was all discovered by statistical physics people, interestingly, a little bit earlier on than McCulloch and Pitts. Boltzmann was one of them, Ludwig Boltzmann, who defined much of thermodynamics. And then there was Josiah Getz, who died in 1903. So these guys were before McCulloch and Pitts, and they were interested in physics, in terms of statistical physics, in terms of atoms and their spins and their probabilistic states and so on, essentially capturing the probability distribution of what has been represented there and in terms of the individuals. And in a way, it turns out that kind of relates back to what the brain is doing. The brain is also figuring out a representation of the world. That's the knowledge, and there is some kind of it is not like extremely deterministic. Exactly this. There's some kind of a probability distribution it captures. Really, is it a probability distribution we capture in our head? Yeah, because when we see a new dog, we are able to recognize it's a dog. We are not, we have never seen that dog before, and we can say it's a dog. So you have some kind of a model in our brain that says what a dog is, and we can assign a probability to the animal. We see, well, that's most likely a dog, right? 98% probability it's a dog. It's not a dog. So on. So it's some kind of a representation of probability distribution that goes on in the brain. So we have these new deep learning models are based on neurons. They are based on probability distribution of neurons. And we have to thank Ludwig Boltzmann and Josiah Willard Gibbs to have invented some of the mechanisms that we use today. Some of you who are familiar with advanced machine learning may remember that Boltzmann comes in because what's called as Boltzmann machines, are the kind of neural networks, and are familiar with Gibbs because there is a number of things have been named after Gibbs, such as Gibbs sampling. When you have a generative model captured, we are able to generate samples and a method called Gibbs sampling. Or there's a kind of probability distribution referred to as a Gibbs distribution, and so on. And the third leg of underpinnings of deep learning are neurobiology, statistical, and physics, and the third is distributed computing. This is about arranging layers in a network and having many neurons in each of these layers are called units computing simultaneously, and all these simultaneous computations layer by layer are all put together, and to determine the final component. There are a lot of theory about distributed computing, such as the universal approximation theorem that says, well, if you had one hidden layer, you are able to compute any function you want to compute. After all of perception and all of language can be thought of as it's a function. All it is it takes as input, a very complicated input. It is mapping it into something that you recognize and so on. So distributed computing does that. So the innovations in the mathematics of distributed computing is good. And the people that have been credited with the most here are contemporaries of ours. Actually, I know them personally. Jan LeCun used to come to my lab. Jeffrey Hinton used to come to my lab. He's in Toronto, not too far from Buffalo. So on. Jan LeCun and I are both working on postal related projects. So the three of them received the 2019 Turing Award for deep learning and neural networks, and for the kind of architecture we just saw here. So those are the modern contributors who are very much with us today. All right, so these are the underpinnings. So how can we compare all of this to databases for dummies and so on? You can see that there is a level of complexity involved, there's a level of science involved, very markedly different than learning HTML or learning about programming languages and so on. There is a lot of underlying mathematics, physics, calculus, linear algebra, the whole works that makes today's machine learning possible. So let's just focus on that one diagram I had on the top right-hand side about deep learning. So there is the diagram of deep learning. I believe this particular diagram I got here is that of a famous architecture called VGG19, which has been put out by a group at Oxford. They have trained a neural network and pre-trained it for you on some scenes and so on, and you can use it to go about doing whatever task that you would like to do. And in a deep learning architecture like this, the world is understood as a hierarchy of concepts. Like at the first layer, you get some things. The input is pixels. These are RGB. There are three layers here: red, green, and blue. And I guess this is the one: 224, 224, 3. And then that is kind of converted into 224 by 224 by 64. So now it's all being brought down with two channels or something. And then you continually reduce the amount of information. Finally, we kind of map it to, well, that's a scene of whatever. Right? So there are so many concepts. You compute edges and then group the edges into regions and regions into understandable parts, and then you say, oh, that's a face. So how these concepts are built on top of each other is the deep, with many layers, and how do you learn the weights? Because these are all the weights are what are needed to convert from one layer to the next layer. You multiply all the input by the weights, and then you add them up and so on. And those weights are learned by a mathematical algorithm called gradient descent, which says the new set of weights at time t plus 1 is the previous set of weights at time t minus epsilon times this symbol here is a derivative in multidimension called a Jacobian of a particular loss function we have to deal with, saying how does the output compare with the input, with the output it should have obtained. If you're trying to train it to recognize cats, it would say, well, how different is it? Then you take the error quantity and then you take the derivative of it. That's where the Jacobian comes into play. And then with a certain learning rate epsilon here, you go and modify the previous set of weights. That gives you the new set of weights at time one. So and this diagram here shows what could be happening. This is in the space or the weight space. The weight space we're using here. And in this weight space, we have a particular point in the loss function we are like, that's the f of x, up among with all these weights here. So that's a pretty high loss. We want to reduce that loss on top here, and this would be we update it. This would be we call it as a gradient step. We keep on moving in that direction. We always try to use the derivative in a negative sign, and we change the previous weights, and hopefully that is taking us towards a lower point here, and says, finally we have reached the lowest point, saying we have learned. That's what the learning is all about. Everything boiled down by using an equation like this. It's a gradient descent learning is what it's referred to, completely based on computing derivatives of a loss function. Okay, so I'm going to now transition into, if you want to learn how this deep learning works, if you want to learn about the particular architecture, if you want to learn about this thing called gradient descent, and a particular algorithm called backpropagation algorithm, and also more generally about statistical models, because deep learning is not just about learning cats and dogs. It's also about learning probability distributions about the world. So that when I'm presented with many examples, I'm not just learning what it is. It could be that I'm doing what's called as unsupervised learning, which is I'm figuring out what this world is like, so that I can do all kinds of inference with it. It's just like a child is observing the world, and it is learning all of it and making a model in the brain. And then when it comes time to do something, it recognizes an object with whatever model it has, and that would be the inference, right? Okay. So how do we learn all of this stuff? What is needed to understand this stuff? Okay, first of all, we need calculus, the role of calculus. Actually, a famous physicist, actually we keep on referring to biology people and physics people, statistical physics people in particular. Richard Feynman won the Nobel Prize for his work in statistical physics. He suggested that the language God talks is calculus. Right? It's not Sanskrit or it's not Latin. He says the language that God talks is calculus. And there's a whole book on this thing. The language God talks on science and religion. That's what science and religion is, calculus. Anyway, in deep learning, this is the language we use. We need derivatives. Right? We need derivatives to figure out how to get the minimum for the loss function. And we need chain rule. That is, we have layers. We don't have a single derivative. We have derivatives. We have inputs going on to other inputs, so on. So we have variables x, y, z, etc. And they are functions of functions of functions. When you have functions of functions of functions and you want to take derivative, we use what's called as a chain rule of calculus, which will say something like dy by dz equal to dy by dx and dx by dz. That's the chain rule of calculus, which is extremely important for this backpropagation learning. We also need to know about optimization, maxima, minima. We have loss functions. How do we minimize that? Take the derivative, set it equal to 0, solve for the parameters and so on. And then we encounter Taylor series. Taylor series, if you might remember that a function is represented by its value at a certain point, and then you need to know the derivative at that point, and you multiply the value of the function by the derivative and so on. So your first derivative, second derivative, and so on. Taylor series gives you an approximation to a function value in terms of a value at another point and the derivative value. So that is again calculus. And then we are not just satisfied with dy by dx. We need multidimensional stuff because our inputs have got so many elements in it. So we have to deal with derivatives, partial derivatives, in terms of, we call them as Jacobians. And we also need second derivatives, not just dy by dx, but d squared y by dx squared in multidimensional format, and we refer to them as the Hessian. So to learn deep learning, you need to be familiar with at least what these terms are. Even the very basic backpropagation will use chain rule, right? So even to get started, you need to know a little bit of this calculus or the language of the gods. Linear algebra plays an extremely central role in machine learning. In what way? We have scalars. These are simple numbers, right? X, Y, Z are all scalar values. We refer to them as zero-dimensional tensors. Tensor is a general term. Or we have one-dimensional arrays. We can refer to them as 1D tensor, which looks like this. It's a sequence of numbers. 2D tensor is a two-dimensional array, like an image, like the picture on your camera, on your mobile phone. A 3D tensor could be the layers corresponding to red, green, and blue together, which constitute the color image. It's not just a grayscale image. We refer to it as a 3D tensor. And we can put together a whole bunch of 3D tensors and call it as a 4D tensor. And that would be like a video. The frames in color would form a 4D tensor. So we can take several videos, I suppose, and call it as a 5D tensors. I don't know, maybe you can go with a 60 tensor and so on. So all of these concepts are needed. So tensor is a common term in deep learning, and there is even a software library that Google provides, and they refer to it as TensorFlow. It's quite a popular software library. And we can refer to these things as fibers of the 3D tensor in different directions. We can refer to them as fibers and so on. And then we have horizontal slices of these 3D tensors. And here are some examples. A one-dimensional tensor is a bunch of a vector here. A two-dimensional tensor is a set of an array here. And a three-dimensional tensor is arrays like this. So manipulating all of these, we're going to be multiplying these values by a matrix. When we go from one layer to the next layer, we are going to be multiplying a tensor at one level and multiplying it by a set of weights to create the tensor at the next level. So we need matrix multiplication. And we also have concepts of transpose of these tensors. And we have concepts of inverse of a matrix or the inverse of these tensors. So all the machinery of linear algebra play a central role in deep learning. So you can't say I won't know anything about linear algebra and I'm doing machine learning. Probability plays an extremely important role as we get into more and more sophisticated machine learning, deep learning techniques. So what kind of probability statistics do you need to know to learn machine learning? Well, we actually begin almost all machine learning algorithms are based on what's called the sum rule of probability and the product rule of probability. What are these? When you have probabilities associated with several variables, how do we combine all of them? And combining them could be done using Bayes' rule. So when you have probability of y given x is the probability of y comma x divided by probability of x. It's called Bayes' rule. And the Bayes' rule can be rearranged to create sum rule, which is when you have a joint probability of two variables, can you tell me the marginal probability of one variable? We sum out the other variable and say, okay, the probability of this variable is this. So product rule is simply to obtain a joint, to multiply the conditional times the marginal. That is, so actually most of the math in machine learning, probability in machine learning is based on sum rule and product rule. And we get into more sophisticated models. Here is a simple neural network. We are the visible units, H are the hidden units. We are going from the visible units as if it were like from the eye. We're getting a input going inside the brain, and we got all these neurons inside the brain which are hidden. We don't know what these are doing, but they are there. So we refer to this machine as a restricted Boltzmann machine. Same old Boltzmann who created thermodynamics, named after him, and we refer to this as well. This is a bunch of variables here. Bunch of variables here. Together, they are actually capturing a probability distribution of observed and hidden variables. And when you have a distribution like that, when you have prescribed all the connections and the weights, it's actually a model. We can refer to it as a Boltzmann model, and we refer to it as a restricted Boltzmann model because the connections are not going every kind of direction. They only go from the visible to the hidden. So it's just one-way direction like that, and there is no connections between the hidden and so on. So it's just called a restricted Boltzmann machine. And a more general version of this, where you have all kinds of connections, like in a brain, it actually is able to capture the joint probability distribution of all the variables observed and hidden. And we refer to that as a Gibbs distribution. Same guy, Josiah Gibbs, we talked about earlier on. He was also playing around with statistical physics, and he was able to say that I can write a joint probability distribution. Y is the output, X is the input, in terms of the conditional probability, in terms of the joint probability, base rule, and you bring in a z of x, and that z of x is called as a partition function. We use a lot of the words in today's machine learning which are completely borrowed from statistical physics. And when Josiah Gibbs was defining a probability distribution like this, he used Z or Z in it, and that's referred to as a partition function. Why do you call it partition function? Because in physics, it was the right way to talk about it. And why do you use the symbol Z for it? That's because in German, partition is said to be Zeistrom or something like that. So today, whenever you find a formulation of a neural network that is capturing a probability distribution, we have Z's all over the place, and Z specifically means partition function, which is because it's called Zeistrom in German. So some of the physics guys who were from Germany, we're talking about 100 years ago when they were doing all this physics, and that's what we're using today. Okay, and today we do something really fancy using probability distributions. We have something called as a generative adversarial network. It's a model that looks at the world and captures a statistical distribution of the world, and it is such a good representation of the world that you can generate samples from it. For instance, you show it photographs of bedrooms in hotels, and it has got all these images. It says, okay, the V's are all the images, and the H's are all the representations of these the world, and then it has got a probability distribution, and then we say, well, give me a sample. When I say give me a sample, it doesn't mean that it's exactly one that you have seen. Give me a sample from what you have understood. It's like showing a human being a whole bunch of cats, or a child, a whole bunch of cats, and then says, okay, draw me a cat. And it will draw a cat, saying this is what my understanding is. It's not going to be an exact image of what you have seen. It says this is what my representation is. And look at these photographs here. These are all samples. These are not real photographs. These are all generated by a model that has learned the statistical distributions of what bedrooms should look like. There's got to be a bed, and there's got to be what, I don't know, a table and so on, and tablecloth and sheets on the bed and all that. It's figured all this out and generates very, very fancy looking images. And all of it is because this thing called a generative adversarial network has all these mathematical models which are based on probability distributions, loss functions. Look at all this. There are derivative symbols here, and there is a loss function, there is a generator model, a discriminator model, all statistically based. And there's a variant of this thing called the variational autoencoder. The word variational comes in because it's about variational physics, or where we are using an idea from probability theory, where we talk about the Kullback-Leibler divergence between two probability distributions. And when you do that kind of analysis, the kind of calculus you use is what's called as a variational calculus. It's not ordinary calculus. It's about functions, function space. In ordinary calculus, we talk about maxima, minima of variables. In variational calculus, we talk about which is the function that's going to maximize a criterion or not. So it's not about variables, but it's about functions. So all of this is all from the domain of probability in statistics, which is the second stool of the field of deep learning. First one was third stool, I suppose. Linear algebra was one, probability theory is another, and the calculus was, of course, the first one. And then the fourth part of what is needed to learn machine learning is computational complexity. It's a regular hardcore computer science topic. And we talk about how when we have a network, if you want to do inference from it, that is, if you want to figure out what's the probability of this combination, or tell me what this is, that these kinds of tasks are called inference. And that problem with these kinds of networks is said to be NP hard, which means it is intractable. That is, as the size of these networks increase, like if they become anywhere close to the human brain, it is impossible to do these kinds of inference tasks, let alone millions or billions of neurons. Even if it is hundreds of neurons, the inference tasks are impossible to do. So you have to develop algorithms that are tractable. Or we have to develop, we just saw what the partition function was. If you want to compute the partition function Z, and you have to compute, and you want to compute the derivatives, you need to compute a derivative involved in the partition function, which involves summation over all possible values. It is intractable. So there are approximate solutions called Monte Carlo methods, which are based on approximating the distribution. So you see, we need to understand a machine learning algorithm. We need calculus, we need linear algebra, you need probability theory, you need computational complexity. Otherwise, you have a very superficial understanding. It's like saying, I'd like to understand the theory of relativity. You know, I don't think there's any book saying theory of relativity for dummies, right? I mean, you really have to understand the concepts there. So it is not absolutely forbidding, but to have an appreciation of why each of these things go together, you got to have a sense of it, right? Anyway, fortunately, a lot of the libraries are all available. The backpropagation is available. You say, look, I'm just not going to want to learn. I can't understand calculus. I can't understand linear algebra, let alone go into Kullback-Leibler divergence and so on. Can you give me a library subroutine? All right, lots of them are available. Deep learning frameworks about 3 years ago. These names keeps changing. There is still TensorFlow is around. There's a Google product over here. TensorFlow. Keras is some kind of a variation of that. That is available. Students seem to like to program in Keras. And the Facebook guys, they developed this PyTorch, which is widely used. Some of these are all like Piano was a university developed one, no longer being used. I don't know any of these are being used. Microsoft and Amazon, these two companies based in Seattle, they seem to work together 3 years ago. They said, okay, let's have our own library for deep learning like TensorFlow, and they called it Fluon. There are other names for it today, MXNet and so on. There are all these libraries available. So we not only need calculus, we not only need linear algebra, we not only need probability theory, we not only need computational complexity. We need to figure out all these libraries, and all these libraries are all library functions for Python. So you need some Python coding for all of this. So these are all the things that go into it. And okay, I still have another maybe 10 minutes to wrap up. So deep learning, is a disruptive technology. It's going to disrupt computer science itself. It's going to disrupt society also. Wow. How do you say that? Well, how does it disrupt computer science? Today, a software developer writes and maintains layers of tangled code. They've written all this logic they've put in with while loops and for loops and tests and so on. Perhaps in the future, it's going to be in the form of a teacher that curates the training data set and analyzes the results and saying, okay, let the program learn all of it does. You don't provide the logic. You're just giving it examples. It is figuring out how to do the logic. The logic is not in the form of logic as we understand it. It's going to be the kind of logic that a neural network understands. All these neurons that are firing from one layer to the next. And by looking at that, you can't understand the logic, what's going on, but it is learning, right? So maybe the software developer is more of curating the training data set. What about mathematics? Today in computer science, we've emphasized logic, right? So we're saying if then else and so on, that type of logic, discrete mathematics, those are the emphasis. But the future is looking more like electrical engineering, probability theory. I guess electrical engineers are quite comfortable with continuous mathematics, probability theory, calculus, linear algebra, and mathematics. Not only that, we also need the computing part, which is the computational complexity. What does NP hard mean, right? You need to have an understanding, because otherwise, that's why you're using this approximate algorithm. Why are you using Monte Carlo? Because it is NP sharp, P complete, we say. P complete is even harder than NP complete. So you have these issues. And in the programming environments, people we have been using our C++, Java. Maybe it's going to be more of TensorFlow, PyTorch, move on. Right? In 10 years, or maybe even sooner, most software jobs won't involve programming, but being able to use these kinds of libraries. And what about hardware? We've been using CPUs. Maybe more of this is going to be GPUs, which are graphics processing units, which do this parallel computation efficiently. That is what is needed. We can also think of this idea I got from a developer who works for Elon Musk in Tesla. And he was saying, he was the software manager for Tesla. He was saying, in my lab, what I put into Tesla cars, we have two types of software. One is software 1.0, which is written by human beings. We refer to it as a classical stack. This code we write using Linux, Apache, MySQL, Python, Perl. So that is all the classical stack. And then he's got, I've got all this software in my lab. All of this goes into the Tesla automobiles. And this is code written by the optimizer. This is the neural network, deep learning network. It is all in a user-unfriendly language. You can't make any sense out of it. There are millions of weights in it. No human being was involved in the coding, and this is what a diagram for that looks like: weights and weights and weights and all these connections. And he's got more of he refers to them as software 1.2 and software 2.2. It's a mix of both of these things. And a lot of people have argued since then that, hey, look, in my lab I also have 1.0 and 2.0, and I think eventually all the 1.0 can be replaced by 2.0. We don't need the conventional human logic. Humans can only think of so many possibilities, whereas this kind of a system can think of all the possibilities and so on. Anyway, it's not very clear whether 1.0 is going to get completely replaced by 2.0, but right now it's a mix of both. So I'm going to purposely conclude, and then we can revisit anything that you might want to ask me about. So my conclusions are that deep learning is a subject inspired by neurobiology, statistical physics, and distributed computing. The new algorithms that are coming out in deep learning, they're coming out every year or every 6 months. There is something that is outdoing what was there before, because some of the brightest minds are now working in this field. The kind of minds that used to do statistical physics and won the Nobel Prizes in physics are all now working on deep learning and winning Turing Awards and so on. And they're all inspired by how it might be in the human brain, that just like we saw about neurons and the computation. And there are many other models and so on. And the kind of logic that we need to understand here is what is involved in calculus, what does linear algebra have to tell us about it, and about probability distributions and statistics, and about computational complexity, and about distributed architectures. So these are the areas that we need to put it together. So, and all of this kind of deep learning will disrupt computer science and will disrupt software development. That is just a prediction for the future, but that seems to be the trend. Until COVID came along, maybe we stopped doing all of that. Before that, we were saying this is definitely going to happen, but maybe it's going to happen. Maybe it's going to get even more accelerated because of COVID, right? Because we need to have fewer human beings doing things and more automation needed. And so all of this is going to get accelerated. All right. So that is my message, that machine learning is not yet another subject in computer science where you can pick up a book such as Networking for Dummies and say, I'll pick up a book on networking and machine learning. Well, you might get a sense for it, but if you really want to understand how to architect a solution, before you say, I'm going to use Monte Carlo inference, or I'm going to use variational inference. Well, you got to know what is Monte Carlo inference is, what is variational inference. And to understand that, you need a sense for the underlying math here. Maybe we can find shortcuts. Perhaps we'll be forced to find the shortcuts. But right now, it is hard to say that I'm going to go machine learning without knowing any of these underlying things. So that's what I think. But maybe you might have another opinion. All right, I'm going to stop here, and I'll let the host moderate any questions that people might have.
Thank you so much, sir. That was a very insightful session, and it was really, really good. So now I request all the attendees, if anybody have any questions or doubts, please feel free to put it in the Q&A section. So before we get any questions, I have one question personally, sir. So,
Okay.
what do you say about what is the scope of hardware industries due to the influence of AI, like maybe VLSI or embedded systems industry?
Okay, very good question. Actually, hardware is needed for all of this. And I happened to read an article, now getting to be a year old now. It's saying that. It was by the research director of Intel, which is the hardware developer, right? And he was being asked as to what are you doing nowadays? And he divided the efforts, research efforts at Intel into something like 3 divisions. And one of which is, we call it as neuromorphic computing, which is computing kind of like the human brain. So, which is even more closer to the human brain than today's deep learning. And he felt that was an important area to model the human brain. I didn't talk about neuromorphic computing today. I talked about neural networks, just fairly simple ideas of matrix multiplication. So, and he said another division they were doing is called probabilistic computing, which he felt is important because it's about the kinds of things I mentioned about probability distributions being captured by graphs where you have nodes corresponding to variables and then edges corresponding to influences of variables. And all the inference you need with these kinds of distributions is all NP hard, NP complete. So you need good algorithms and hardware to do it approximately. And he felt that computing or inference, you've learned all this stuff quickly, like we do, right? We have studied a lot, but when we are asked a question, we are able to provide an answer fairly quickly and not having to churn through a whole lot. Maybe occasionally we have to do that, but we would like computers to be able to do inference over probability distribution. So his second area of Intel's hardware development was to do probabilistic computing. And the third area for Intel was quantum computing, which is a totally new paradigm where we are not using discrete states, but we are dealing with states in between. Things can have multiple states and so on. So that's another physics area. So Intel being a company with probably a lot of physicists, so there are physics people doing that part. So we, coming from the computing side of things, probably relate more to the other two. Maybe the probabilistic first, neuromorphic also is brain-like, and maybe the stuff about doing distributed computing efficiently is a monopoly by NVIDIA. Right, NVIDIA is the one that does all the GPUs and things like that. didn't sound like Intel was bothering itself to compete with NVIDIA, which is doing all the GPUs necessary for deep learning. But I'm sure there are some niche areas there also that maybe Intel is not doing, but other companies might be saying, we could do this for neural computing, today's neural computing. So there's a scope for all of these areas for people interested in the physics and the hardware. Okay?
Okay, so thank you so much. Now we have a few questions. There's one question from Gausia. The question is, please highlight on the use of weights in deep learning.
Please highlight weights in what?
Please highlight on the use of weights in deep learning.
Oh, use of weights in deep learning. Well, that is a central part of deep learning, of any kind of neural network learning. It is, you have an input, let's say you have a set of values with input. With a binary black and white image, you have an array of pixel values, every one of them is 0 or 1, right? So that's the raw input you have. And those have to be mapped eventually into an output. The most famous data set is the MNIST handwritten digits, 0 through 9. I've got an image of 0 through 9. I want to, the output should be to give a 10-dimensional vector, which is the probability of 0 and 1 and 2 and 3, so that the sum of the probabilities add up to 1, right? That is the input and that's the output. In deep learning, we would have a layer in between, or more layers in between, which actually convert the image into something in between. So it represents them in terms of features, some set of values. And why do we do that? Is so that the final classification problem 0 to 10 can be solved easily by a simple classifier called a linear classifier. Whereas the raw input, which all the, if supposing it is like 28 by 28 grid on which we have a handwritten digit, that's that many pixel values, 28 and 28, whatever that is, 726 or something. And that's a large number of inputs. Maybe we'll reduce it to 700 or how about reducing it to 100 or maybe even 50. And then from that representation, it's a simple classification that partitions the space here in 50-dimensional space. And so how do we go from one layer to the next layer is based on the weights. And how do we get the weights? The weights are obtained by having a training data set which presents an input, and then there is a correct output. We have a sample of a 7 as input, and the output we say the answer should be 7. This means the output at 7 should be high, and outputs at all other 10 possibilities should be low. And if the output is giving you some wrong answer, we have to compare the correct answer to the wrong answer, saying how much are you off? And so we need to use that and use a function called the loss function. We need to take the derivative of the loss function. The derivative is what is going to be used to update the weights through the back. It's called back propagation. We go from the output going backwards and backwards and backwards. And so we update the weights. And we keep doing this again and again and again with several presentations of the inputs. And when it gets most of it right, we say, there we are. So we figured out the weights. The weights are what convert the input to the next layer. And then there is the weights that convert from that layer to the next layer, like that. So weights are the central part of learning. So we have to understand what the weights are, and the backward propagation algorithm called backprop. That again is based on computational complexity. Ordinary gradient descent by saying, okay, just take the gradient and change things back, but that is computationally complex of order of W cubed, and it reduced to W squared by using the back propagation algorithm, which by the way was invented by Geoffrey Hinton, who won the Turing Award. He came up with that idea of how to do this efficiently. Okay.
Yes, sir. Thank you so much. I think that question is answered. The next question is from Mr. Sanjay R. The question is, why isn't there many applications of reinforcement learning in real life?
Oh, okay. Yeah, the whole sub-area of machine learning is reinforcement learning. People kind of break it into machine learning into three parts. There is supervised learning, there is unsupervised learning, maybe there is some variations called semi-supervised learning or self-supervised learning, and then there is a whole area called reinforcement learning. So reinforcement learning is something very natural for us human beings to think of. It is how does a dog learn to go and fetch your slippers? That is, when the dog brings the slippers to you, you give it a reward, and there is a reinforcement. When it does something else, you don't give it a reward. So it says, aha, I should bring the slippers. That's how it learns. So the learning that goes on there is reinforcement learning. What about with computers? There are many good applications, and a lot of them in these video games. That is, you want a video game to win, and you're not telling it what is exactly your behavior, and it has to play games, and it says, okay, if I went here, went there, I seem to have a reward, I seem to win the game, and it keeps on learning from these experiences to become a good video game player. And so we need an environment that gives it some kind of feedback, saying by doing this, I learned. So that is the biggest beneficiary of reinforcement learning. But today there is many other applications, and there is also an area called deep reinforcement learning. That seems to be a simple thing, like your environment is all processed by deep learning, like your video game screen is processed by a deep learning mechanism that brings you a whole bunch of features, and then you use the mechanism of reinforcement learning, which is based on actions and rewards. And deep learning algorithms have a couple of different methods they use within. One is called as exploration, the other one is called exploitation. That is, it will try and make a move. The video game says, what if I try and make this move? I've never done this before. And if it gets a bad reinforcement, it says, oh, okay, I should do that. Or if it gets a good reinforcement, hey, great, I learned something new by trying it out. Because human beings do that also, right? We are trying to learn some new software, and if we try something that has good results, we will try and remember it. If we don't get good results, we won't do it. So that is the kind of thing. And exploration is to try out new ideas you haven't done before. Exploitation is, I've done this before, it works well, I'm going to use it. So you're being conservative and you exploit what you know. So there are these modes of learning within reinforcement learning, and those can be used. Only thing is you have to think of where is the good application. Video games, no question, is a good application. There are also cases of reinforcement learning being used in recommendation systems. Recommendation systems is about Amazon telling you that people who bought this item also bought this other item. And there again, it could be using reinforcement learning, saying, should I be recommending this, or I'm going to turn off this customer and try it out. So it could use reinforcement. So reinforcement learning could be used within recommendation systems outside of the video game domain. There's got to be many others, but it's a very specialized area of machine learning, and it has been around for a very long time. I've been a student of machine learning for about 50 years. Reinforcement learning has been there for about 40 years or something. It's been around, but it's not in the mainstream. But there's a lot of potential. And game playing, as I said, the AlphaGo, the program that beat the world Go master, AlphaGo was based on deep learning and reinforcement learning. So in that scenario, it did extremely well. Okay.
Yes, thank you, sir. The next question is from Veena GS. What's your take on AlexNet, ResNet, and Boronet?
Oh, okay. Well, you are exposing my knowledge of very, very current deep learning. Deep learning is very, very rapidly expanding field. AlexNet is named after one of the colleagues of Jeffrey Hinton, I believe. So he has a particular architecture with a particular. So what happens in practical machine learning is you ask these questions: what architecture should I use? How many layers should I use? Or you would say, what is the loss function I should use? And what is the optimization algorithm I must use? So you have all these kinds of issues, and you make a certain set of choices, and that seems to have been made by AlexNet. I don't recall offhand what exactly the choices that Alex, I believe, is his first name. His last name is a complicated Russian name. And as far as the REST net is an interesting one, which is residual net, which is taking the output some of earlier units and bypassing some of the units along the way and feeding it back again. So it's like having a bit of memory of what came before. So you're not completely forgetting it. The disadvantage of an ordinary network, which is feed-forward network, is an ordinary feed-forward network could be, you process and you get some information, you forget about the past, and then you move on, and maybe there's some value in bringing in some memory of what was it earlier like, and that seemed to have even tremendous advantages. So I don't have any more specific answer than that, but ResNet, from what I can tell, is extremely popular. I don't know about the Boronet you mentioned. It's probably named after a person. Okay, so I must excuse myself on that. Boronet, is it a Boro? Yeah. Anyway, I'll stop there on that answer.
Okay, sir, thank you. And the next question is from Sudhir P. Post-COVID, more AI will be focused towards disease diagnostics, patient health monitoring, etc. What's your opinion?
Oh, yeah, there is post-COVID lots of projects going on in the US, for example. Plenty of funding for anybody saying, I'll do COVID. Okay, we'll get funding for you. Uh, so many things can be done, right, at the level of the signal or the images and all that, and also at the level of pure raw data, where you might have a mixture of data types. You have scans and you have diagnostics, blood pressure. So many inputs come in, and you need to integrate them all. It's not just like a one image we're processing. So some of these more sophisticated architectures that are available today, particularly probabilistic graphical models that I mentioned, they can deal with variables. You can have a system that you have all these heterogeneous type of variables coming into the same system, and you're trying to figure out what is the distribution of all of this, and you're able to make predictions. And also, many of the terminologies that are used in pattern recognition machine learning are of great value in this COVID testing and all that. I'll give you a simple example here. So if you have 5% of the population is infected, and you have a test that is 90% accurate, giving you two pieces of information. 5% of the population have been infected with COVID, and you have a test that is accurate 90% of it. 90% of the time it gives you the right answer, whether the person is positive or negative, but 10% it may be a mistake. Okay, fine, we got a test that is 90% accurate in the population, and then I take a test and it comes out positive. Wow, it's positive. So how sure am I that I've got COVID? Right? And when I ask you that question, how sure should I be? The obvious answer from somebody would be, well, that's 90% good, right? Maybe you should be 90% sure that it's correct. Actually, the answer is very different. The answer is that there is only 33% confidence that I've got COVID. There's 67% probability that I don't have COVID. Really? Yep. A person who is familiar with pattern recognition machine learning will tell you why that came out like that. Because they're familiar with these terms called precision and recall. All right. In a Google search, we talk about how good is the search engine. You calculate its precision and you calculate its recall, and which involves true positive, false positive. And so it is based on those ideas. And medical terminology and pattern recognition terminology, we use different words. When we say precision, they call it as positive predictive value. And when we say recall, they will say that is sensitivity of the test. The same thing. So we use different terminology, and we are very familiar with these terminology. Those of us working on pattern recognition, machine learning. So we can bring these kinds of things also to play a role. So our knowledge of probability will be very useful in the COVID world. And not only that, it's our deep learning is going to be useful in the COVID world because of dealing with images. Maybe they use chest X-rays, right? They use the chest X-rays or magnets are useful. It is also useful just for simple reasoning, saying we actually can deal with the complicated probability distribution. One variable is yes or no. Another variable is a continuous value, which is like temperature or blood pressure. And then another variable is multi-value. All of these, how to deal with all of it, to make inference, that is, how to make a good conclusion. We have powerful tools that can become useful, even at the fundamental level, that we have a good understanding of what does it mean from the positive value of a test. So, yeah.
Thank you, sir. The next question is, can we apply ML and AI in motorsports like race cars, etc.?
All right. This is the beauty of this working with machine learning in AI. You can use it in anything you can think of. And the beauty of it is, previously we could have said, well, you could have done it 50 years ago. Only thing is, I would have had to design handcrafted features. You got to know about motor cars and motor car sports and all this, and you would have to laboriously figure out all the features from whatever the inputs you have, all the cameras, and it would take you 20 years to come up with a good algorithm for doing that. The beauty of machine learning is, okay, you can have a supervised data set and saying, okay, here are all the examples, and here is what it should do in all of the situations. Or maybe you can drive the car around and show it what it should do. It will record you how you did, what you did, when you saw something. And it seems like an application, and that's where so much effort has gone in, right? Tesla and all these companies. Every company was invested in autonomous vehicles. I don't know if any of them were serious about motor car racing and all that, but I'm sure that that would just be another step if society would really say that that's a good way of spending your resources. Okay, yeah.
Yes, so next we have a question from Nikhil Agarwal. How to choose a better framework for learning? How to choose between Google Keras or Amazon frameworks and Facebook PyTorch and others?
Okay, that's a good practical question. I have to ask my students these kinds of questions. They're the ones who implement these things. I just observe what they've chosen. I usually say you can go and choose your favorite library and come back. GitHub is an influencer. So when you go to GitHub, usually they start out with a paper saying, what is the topic? Let's say motorsports. Okay, go and see. Has someone written a paper on that? Quite likely there will be a paper on it. And in that paper, nowadays, you need to have an appendix which gives you all the code, and the code might direct you saying, well, that code was all in Keras. Keras seems to be extremely popular. TensorFlow is a little bit harder to work with here. And PyTorch is, of course, there are also versions, right? Keras 2.0 and all that. And then PyTorch similarly was easier than TensorFlow. And then usually easier, harder means you can have more flexibility. Things easier is to figure out all the common things. And so it seems like a few of these. I don't know what else is happening on the Amazon Microsoft front. I don't know what those researchers are using. Are they using anything like Bluemon or some variety of it? I'm not sure about it. But yeah, all these libraries are there, including TensorFlow. So go look there and where you're starting from. Okay?
Yes, so thank you so much. Next, we have a question from Maya Madam. The question is, can you suggest when to use bidirectional model?
When to use what Excel?
Bidirectional model.
Oh, bidirectional. Okay, very good question. There is. I also thought it was just a little cute area. I mean, I knew about bidirectional long ago. That is when you are trying to recognize handwritten characters left to right. Well, would you recognize them right to left? I'd find just some variant. And like you are trying to translate from one language to another, machine translation. I could go about left to right, or I could also use right to left, or trying to figure out parts of speech, left to right or right to left. Bidirectional says do both. go left to right and go right to left. And today, with computing power not being such an issue, bidirectional has caught on in a big way, saying there's a lot to be gained by looking at later words, later parts, to infer what the earlier parts should be. Which kind of makes sense that when we are reading something, we might not understand some word or some concept, but as we go along and read a little bit more, it becomes quite clear. Oh, that was what that earlier concept was. The earlier part did not allow us to understand what you said. It's just like Alexa was trying to understand what you said to on the microphone, and you are not very clear, but later on it figures out that's what you said. Okay, so now I understand what you're saying. So a famous natural language processing program, which has been revolutionary for the NLP people, called BERT, BERT, and the B stands for bidirectional, right? So bidirectional, I don't know what all ERT stands. I think T stands for transformer, and it uses the idea of attention models, where it keeps track of what is the past with a summary of what has been happening. And not only do you keep track from left to right, but also right to left. And so Bert says the important things were bidirectionality and the transformer representation. And that led to a revolution in natural language processing. It's a Google product. Their paper is written by a dozen people or so. And it seems to be the state of the art for natural language processing. It's all based on bidirectionality. And I've just gave you the intuition why bidirectional. Okay.
Thank you, sir. We have a question from Kushagra Avasti. What is the number of hidden layers appropriate for a deep learning model, and how does it affect our model?
Yeah, very good question. Oh, yeah, because when we talk deep learning, you say, okay, what is depth? What should be the depth, right? I suppose how deep a hole do you dig when you're doing a planting in your yard or your farm? Well, okay, it's got to be twice as big as the root ball of your plant, right? If it's a tree, it's got to be a big hole. I guess depth has something to do with your task at hand. And here again, depth is supposed to give you exponentially good results. So if you have a depth of 1, that is the minimum depth, because you can't even do certain tasks without a single hidden layer. If I don't have any hidden layer at all, I can only do linear combinations. I can't even compute exclusive OR without a single hidden layer. Exclusive OR is a non-linear type of transformation. So you need 1 layer. And universal approximation theorem says, well, all you need is 1 layer, and I can compute any function you want. Okay? So any complicated function, everything is a function, right? Input to output, that is a function, however complicated. It's a function. I can compute any function to arbitrary accuracy by 1 layer. Only catch here is that could be infinitely large number of units. That is useless. I tell you that I need 1 lakh crore. That's the new word I learned after coming to India. What is 1 lakh crore, right? 10 to the 12, 1 trillion. I need 1 trillion units. That's no good. But if you add some depth to it, that's going to dramatically reduce. How many units do you need? Oh, that's great. I could do 2. I could do 3, maybe even more reduction. So you're going to add, so there is an exponential relationship as you go from one to the next. The gain you're going to have is of the nature that is exponential. It's not like a linear, it's exponential. So dramatically, a trillion goes into a billion goes into a million. Like that, it's going to jump by orders of magnitude when you add these depths. Of course, when you add these depths, you run into all kinds of other issues for gradient descent. When you do backdrop, you run into issues such as vanishing gradients. You're trying to train the network for these weights, and there are so many levels. The chain rule of calculus is operating from one layer to the next layer. What's going to happen is you're multiplying the 0.02 by 0.02, 0.00004, and the 0.00004 by 0.00004. going to be 0.0000000. It's all zeros. So you have no computation possible. That there is no gradient, nothing is changing. Your weight is fixed. So you run into these kinds. So what should be the depth? So the depth has got to be some trade-off between how many layers you can have and the sophistication you have in doing that prop. So I don't see people using exponential number of layers. It's like I have a million layers or anything. The order of tens or twenties of layers. And again, as you add layers, you get that many parameters, right, to deal with. So when you multiply one set of units to the next set of units, you have that many weights. So that's not that right. You go from 20 to 10. How many weights do you need? That's 20 times 10. That you need 200 weights to go from 20 to 10. So that's product and product like that. So all of this is constrained by practical considerations such as the number of computing units and practical considerations such as vanishing gradients. Of course, there are all answers to these questions too. People are working on these things, like how to deal with vanishing gradients and so on. But so you kind of stick to some reasonable numbers. Okay, how many weights are there, and how long does it take to train? And is this application so critical that I don't mind spending a week on training it, or do I have to just train it within a few hours? So you're gonna say that's all. Okay.
Yes, sir. Thank you. Next up, we have a question from Irana. Can deep learning be used for unsupervised learning?
Oh, good question. Uh, People think of machine learning as supervised learning. That's the most famous example. I take a handwritten digit. It's got to be able to say, is it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? Which one is it? That is supervised learning because I train it by giving those examples. Unsupervised learning is I simply give you 0 through 9 handwritten digits. I don't tell you which one is which. Unsupervised learning has to figure out, well, how many classes of data exist. Hopefully it will come out and say, well, it looks like there are 10 classes. It's like somebody who doesn't speak Chinese and I throw you a whole bunch of Chinese characters at you. You have no idea what those Chinese characters are, but you might be able to assemble them saying, okay, these things look similar, these things look similar. I'm going to do unsupervised Chinese learning and nobody telling me about Chinese. At least I've figured out how many clusters there are. And we say there seem to be this many groupings of characters. And then, so the same thing can be done with deep learning. I mentioned the restricted Boltzmann machine today. We have visible units and hidden units. We can train such a network using unsupervised learning, where it's got to figure out what those hidden units are that best characterize the observables. How do we do that without any kind of supervision? You can do that by saying it should capture the probability distribution. So there is a certain probability distribution that data represents. And visible units are, of course, what is observed, maybe the pixel values or other features. And it is supposed to capture the distribution, except the distribution now has some variables that are observed, some variables that are not observed. And over this, we need to find out a joint distribution that captures the data. And so we end up with having the joint distribution characterized by the conditional distribution. And so the simplest unsupervised learning model is a restricted Boltzmann machine, RBM. And how do we train an RBM? We set up a maximum likelihood criterion. We say we want to learn a probability distribution. We say, well, in this case, when you observe data, you should assign to it the highest possible probability. That's called maximum likelihood. The standard classical technique of parameter estimation in statistics. I give you a bunch of data and ask you, what is the mean of this distribution? How do you figure out what is the mean? Well, I set it up as a likelihood function for the data, and then we say it should maximize it on this observable data set, and we assume all the samples are identical, independently distributed. So we talk about the likelihood is being all the product of the probability of the data, and we need to maximize that with the parameters. Same thing is going on here. We do maximum likelihood estimation. And how do you do maximum likelihood estimation with a network? You would say, well, compute derivatives. Aha. So the same idea of derivatives comes into play in unsupervised learning, like it does in supervised learning. End goal is to get a nice model. model is simply a probability distribution of the data, except the variables are kind of structured in a peculiar way rather than any free variable. Okay, so unsupervised learning can be done using deep learning. And I just gave you a very, very simple example. All the excitement today in machine learning, deep learning, or most of it is in this area called GANs. They're all unsupervised learning methods. They're all learning distributions of different data so that they can generate beautiful photographs. They can generate very natural looking sentences, and people have been misusing them by doing fake news and all that. You can generate whatever article you want, simply saying, okay, generate all this, I give you some cues, and they can generate stuff which is all nonsense, and people start sending it on their WhatsApp, right? They say, well, I got this on WhatsApp. It was all generated by a generative model. Nobody did it, but it created all this kind of stuff. Anyway, that's the humor of it. But yeah, unsupervised learning is a big application. Okay.
Thank you, sir. Next, we have a question from Samra Das. What would be the role of a software developer when software 2.0 comes into the picture?
Okay, this is a little scaremongering point that I made. I was wondering whether I should even say it. Uh, this was done by, as I said, the Alexa chief. No, not the Alexa chief. The guy at Tesla. Tesla, right? And he was just observing that in his lab he's got 1.0 and 2.0, and then people all started chiming in his blog, saying, "Oh, I'm the manager at Google, and I tell you, all the software we have at Google, most of the 1.0 could have been replaced by 2.0." We made a comment like that, and so wow, really, this means 1.0 is going to get replaced. There's going to be no need for programmers, and all we need is 2.0. Anyway, the jury is not out on that clearly. That there is still, for the next decade, there's going to be human-generated code. But the direction you can see is automate more and more things. And this automated stuff is going to be easier to do because the machine learning tools can do it for you. We don't have to have everybody figuring out and scratching their heads and thinking of all the alternatives that, or maybe debug it by fixing it, saying, "Oh, nobody ever thought of that combination." So on. That is why it's called spaghetti code. And by having this in a neural network, we just need to train it with more samples. So the programmer is a good curator, which is supplying lots and lots of data, and not doing any logic as such. Well, I would say you need, at this point, you need a healthy dose of both. I would not abandon conventional programming, the regular programming 1.0, but be aware of 2.0 because every piece of code you write is going to involve two parts. One part is 1.0, one part is the curation and feeding the data and all that. But to be aware of 2.0. So for the next, I would say five years or so, unless everything is accelerated so fast that AI completely replaces. But yeah, the future then the human's role would be data curation. That is collecting all the data and providing it in a proper format, and the auto encoder is crunching away at it. It's figuring out what to do, and you can only think of it if we specify what the tasks should be. Maybe we need to give it some guidelines. This is where Elon Musk stuff comes in. Elon Musk, the boss of the guy who says there's 1.0, 2.0, Elon Musk is afraid that machines are going to take over the world, right? And others are saying, wow, being alarmist, saying we just need to tell it, okay, don't do this kind of stuff. Right? Anyway, we're getting into a little of speculation, but yeah, that's where we're going to be heading. But don't get too worried right now. Okay.
Okay, so thank you. So due to the time constraint, we'll be having the last question of the Q&A session. It's from Sudanva. The question is, what is the scope of deep learning in network security?
Oh, okay. Yeah, I'm not an expert in network security other than being a lay user, but I know some of my colleagues, they keep on telling me, oh, we're using machine learning in network security, where, for example, one application would be anomalous behavior. That is, we have a network and there are some things happening which are not common, which means the machine learning system has figured out the probability distribution of what kind of activities are normal. And now comes an activity, maybe it's a sequence of actions that is abnormal. And how does it know it is abnormal? So it would have to have a probability distribution. Like let's say it's a Gaussian distribution, and there is a peak to it, and either tail is the abnormal, and if it is falling way outside of the tail, then it is really abnormal. So if you have here is in a case of unsupervised learning, it is just being given examples of this is what all the actions are. It's figured out the distribution, and the purpose of the distribution is when I give you a new sample, please tell me its probability. That's all we're asking for. So that's a classic use of a generative model to tell you the probability. And say, okay, there is an anomalous behavior, so network security would be alerted. And what is, okay, as long as I'm on the topic of what is a generative model useful for? One is this one, to give you a probability of an event. The other one is to generate a sample. So I'm not so interested in giving me numbers. Like probability is not of interest to me. Given a new phase, what is the probability of this phase? Well, that's a probability of 0.001. Well, that's useless to tell me that this phase is such a low probability. What is more interesting is give me a new phase. So it says, okay, I'll give you a new phase, and I'll generate phases for you according to the probability model. And those are all very interesting to look at. There no such person exists, and it is saying this is a realistic person that doesn't exist, but it is a part of my problem. So anyway, anomalous behavior is an application of deep learning.
Okay, so thank you so much. The question and Q&A session was very good. So now I'll hand it over to Setu Selvi madam and Shobha madam to thank you and end the session.
Okay, thank you. You are a great host. I'm glad you moderated the questions and gave them to me clearly so I could answer them. Thank you.
Thank you, sir. The honor is mine. Over to Setu Selvi madam and Shobha madam.
Do I need to cede control?
No, sir. Are you hearing me?
Hello, is that Setu?
Yes, sir.
Oh, okay, now the microphone is better. Yeah, Setu,
Yes.
first of all, I'd like to thank you for inviting me. I had
No
fun.
problem.
Great questions. Yeah.
Yeah. So there were about 200 participants. I think everybody are taking home a message from you on deep learning and machine learning. Thanks a lot, sir.
Hey, Setu, thank you very much. It was your initiative. You approached me, visited me, and really encouraged me and cajoled me into taking this on. It turned out to be not a chore, but an interesting experience for me. I was going to share this recording with many of my colleagues at my university in the US. Everybody is demanding machine learning, and everybody's saying, can I teach it? Can I do it? Can we have like 100 versions of machine learning in every department? And I'm just saying, look, there is a certain amount of expertise you need in all of these. You can't simply say this is just another application like I'm going to learn Python programming. I can't make that point here. This is what I'm going to have to tell them. I don't know if they'll buy it from me, saying it would be possible to walk in and do machine learning.
Machine learning.
3 days reading of Machine Learning for Dummies book, right?
Yes, sir. I think that is not possible at all. It's really that you have to dig into the subject and then only start teaching it.
Yeah. Of course, the teachers of machine learning have to work hard at converting this.
It's not so easy,
right?
sir. Yeah.
Yeah, I have tried to understand theory of relativity many times.
Oh, that's not our cup of tea, I think, sir.
Right? I don't know how many people can say they tried to understand it and actually understood it.
Okay. Oh, thanks a lot, sir. I think all the participants also like the webinar. Thanks a lot, sir, again.
Yeah.
Shobha, you have
Wonderful.
something to tell?
Best to all of you, and keep in touch if it's feedback that I can use. Okay? Thank you.
Yes, sir. Thank you, sir. Shobha, have you anything to tell? Shashank?
I don't know, ma'am. I think her mic is not on.
Okay. No problem.
I can hear you. I can hear you.
No, sir, there is another madam, IEEE RIT chapter advisor is there, Shobha madam. We were just thinking that whether she is going to talk, but I think her mic is it's not muted or something like that. No problem, sir. We will end this
Okay.
session.
Yes, ma'am. We'll end the session. So thank you so much once again for this session. It was really wonderful. So most of us got a good insight about the subject. So thank you, sir.
Okay, very good. Good luck to all of you and stay healthy and hope everything works out soon. And okay, we'll be in touch. Okay?
Yes,
Yeah.
sir. Thank you, sir.
All right.
See you on Monday, sir. On your
Yeah,
class.
Monday, Setu is my student in my class. Thanks for coming to my class. Any of you are welcome. All right. If you want to be on my Zoom class, let me know. Or you can always join on Facebook, which anybody can watch at 11 o'clock Mondays and Wednesdays. Okay?
Yes, sir. Yes, sir. Thank
Thank
you,
you,
sir.
sir. Thank you.
Okay. Bye.
Bye, sir.